Hello, sir.
Yeah.
Hello, sir. We are live now. Vinay, sir, can you please introduce Deepak, sir, to our attendees, sir? Hello, Vinay, sir. Hello, Vinay, sir.
Geeta, are we ready to start?
Hello. Can you hear me, sir?
Deepak, start. Sure.
Okay.
So I just
Give 1 minute. Yes, sir.
give it 2 minutes.
Yeah.
Yeah. So it's April and I'm glad to introduce Deepak. I'm glad 1990 currently Vice President at Hardware Ventures. He has over gives experience of leading firms like he is here to share his experience insights into emerging semiconductor trends, chip design ecosystem, and skills needed to his field. So over to you, Deepak, and thanks for joining.
Thank you. Thank you, sir, for kind introduction. And thanks for giving me opportunity for this presentation. So, um, as I just said, my main goal here is to share my experience um, with everyone, and the slides are just bringing the talking point. But I would like participants to stop me and ask question as much as possible. Um, uh, so, because I have worked in various companies and across various technology nodes, and the technology has been evolving year by year very rapidly. So I would be able to give some overview on that. So is my screen visible? The slides. Sir, is it visible?
Yes, sir, the slides are visible.
Okay, okay. If you face any issue in hearing me or slides, just feel free to speak up. Huh? Okay, okay. Thanks. Good morning, all, and respected faculty members. I'm going to present about semiconductor testing, and I'll touch upon a little bit on the advanced technologies. Some of these topics you must have already read about it and maybe also covered as part of the previous presentation. Uh, and as I just said, right, I would like to give more practical aspects on these areas. So feel free to ask questions. Okay. So before I jump to the testing, I would like to spend few minutes on how the semiconductor industry is moving and what are the challenges today, and even a little bit about the India aspect of it, right? So, as part of the first few slides, I'll cover the semiconductor market, technology trend, challenges, and the path forward. So, here is the current overview of the market, semiconductor market. So, in 2023, we had a total revenue of semiconductor industry around 545 billion, and it is further increase in 2024. I don't have the number today with me, but it is beyond 600 billion, and the revenue is rapidly increasing. Now you see the share of the companies. The today Nvidia is becoming the most valuable company, not just in semiconductor but overall a list of companies. And this is the first time any semiconductor company has become the most valuable company in the world. And this is a historical moment really for this industry. Okay. So the composition of the product has been changing decade by decade. Like currently, the GPUs or the AI is the main focus area, and that volume or the revenue is growing rapidly in this direction. But last decade, it was more focused on automobile, and prior to that, the more focus was on the telecom. So every few years, there is a change in focus. Accordingly, the companies grow at a different rate. And I'll just bring one slide on the India opportunity. So India has most of the companies, semiconductor company present, have their R&D center. Like at least all top 15 companies are present in India, and they have significant population. And India is the single biggest country for the semiconductor design. Currently, the semiconductor design engineer population in India is 1,25,000 approximately, which is the 20% of the worldwide design engineers, and it is highest, even higher than US or China. And Government of India has launched Semiconductor Mission in 2021, where they are sharing a lot of support. They are supporting in terms of monetary, in terms of knowledge, and even in terms of bringing business. to semiconductor industry, and many companies have taken this support like DLI, design link incentive, and the PLI, production link incentive. So for example, they have given 2 million of DLI for each company whosoever is designing the product, and a lot of free tools, which is a great support for any company to start, because it's a very high investment industry. For any semiconductor product to be designed, even if it is a very simple product, it needs at least $10 million, right? So it's not very easy to secure this money, and government of India is now helping in this. And the focus in India is being shifted from service-based startup to product-based startup. There are a lot of service company who do resource augmentation. These have been in existence since last 20 years, but in last 3-4 years, a lot of companies have taken this step forward to design the product. And as I said, right, it needs a lot of investment, so it's not an easy task. It needs not just the money, but also the customer who are ready to give you a lot of volumes, because you need the volumes in terms of few million chips for a chip to be profitable in production. So it needs a lot of effort, but people are taking step forward toward making India self-reliant. And hardware, my company which I joined about a year back, is also one of them. We are a startup which is developing a semiconductor product in India, start from scratch, and we plan to launch this product sometime next year. Okay, just a quick view of the evolution of silicon nodes. Most of you might be aware of it. So if I go back to 1996, 250 nanometer, and that is a product I worked on as my first career chip. I joined the industry in around 2000, and that time I was working on 180 nanometer, and starting from there, coming to 5 nanometer, what I worked in 2 years back in Samsung as part of the storage chip. So I worked across various nodes, and these are not just the nodes. There is also underlying technology keep has been changing over years. So when we were in 180 or 250, it was like planar technology. Coming to 16 nanometer onwards become the FinFET, and 3 nanometer onwards become gate all around. So there is a continuous change in terms of the gate density, as well as the power consumption of each transistor. That is on the technology side. But at the same time, the number of gates needed to implement the functionality, the kind of functionality we want to achieve in a chip, has grown exponentially over years. While the chip might be having few hundred K transistors or gates in 1996, today it's a billion transistor in the chip. Especially in GPUs, it is multi-billion transistor. So that is the reason it requires technology to evolve every day, every year. And when the technology evolves, the technology we are trying to achieve higher speed, lower power, more density, the testing becomes even more difficult. The probability of faults increases, and the variation of process across a specific chip also increases, and that brings more challenges to the testing industry. Designing new algorithm, ensuring we catch all the faults before the chip goes to customer, becomes more and more important, right? So I'll talk about it in coming slides, but just want to give an overview why testing has a bearing on the silicon nodes. So yeah, as I just said, right, the technology, though we have started from 250, I mean, as far as I've seen myself, though we started even beyond smaller nodes also, bigger nodes also. So earlier we had planar technology, and 250 to 28 nanometer. Then we moved to 16 nanometer onwards in the FinFET. The reason is planar technology has limited control over gate, and the leakage was high. And when we got FinFET, the gate control become higher, so the leakage reduced, because in planar technology or the lower node, the dynamic power was very high as compared to leakage. But as we go on our lower nodes, even the leakage, the dynamic power is reducing because the voltage is reduced. Here we were supplying like 1.5 volt or 2 volt for the digital logic. Even, like in 90 nanometers 1.5, in some of the technology like 28 nanometers 1.2 volt. But here we are supplying around zero point 0.8 volt, zero point 0.7 volt to the digital logic. So the voltage is reduced, which results in the lower dynamic power. And then leakage, proportion of the leakage power becomes high, and that makes it very important that leakage power is reduced. So that's where the FinFET technology came in, where we have better control on gate. But as we go even further lower nodes, the criticality of gate control becomes even higher. The leakage has to be further reduced, the speed has to be further increased. So the technology is moved to the gate all around. So this is where we are today. The gate all around technology is being implemented in all the latest node 3 nanometer onwards. Okay. So apart from the chip, the package is equally evolving over years. So back in 1970, I think this kind of package you would have seen while doing the projects. 555 timer. I remember I used that as one of my first chip in the college doing my first project. Those are DIB, very simple package, simple chips. But as the chip sizes increases, as the power consumption increases, the real estate on the PCB, the area chip is taking on PCB becomes very critical. We want the package to be as small as possible, and it should be able to support the heat dissipation being done by the chip, because package should conduct the heat outside. The difference in the ambient temperature and the junction temperature should be minimized. Otherwise, your performance of the chip will not be optimal, right? So, considering these facts, the packages has been evolving over years. Like DIP was one of the first one. Then QFN became very popular. Quad flat no lead package. It does not have the leads like this, but it is very thin and kind of seamless to integrate on the PCB. Then came up the 3D system in package where multiple chips are being used. And then latest trend is wafer level package or 2.5D or 3D circuits where chips are stacked over each other in a single package. Like here, there will be a base die and then multiple die will be stacked. Here, multiple die will be stacked over each other. So why this is needed, I'll touch upon in the next slide, why this latest trend is coming in where we need this kind of packaging. And again, coming back to testing, the packaging has equally adding the challenges, because when it comes to the bigger size of package, you need to ensure that our tester, the ATE equipment, automatic test equipment, is able to support. Suppose a chip has 20 pins, I can easily test them on a tester. But if chip has say 500 pins, then it becomes very costly and very difficult for me to test that chip, because my ATE, the test equipment, may not have so many channels. It may not be able to control all 500 pins. Or if I design that kind of a tester, it will be very expensive. So these all brings new level of challenges. When we go to the 3D or 2.5D integrated circuit, here again a different kind of challenge come, because each die first has to be tested independently, and then we need to test the interface between each die. So that is a different test technique, and the fault type could be completely different in the inter-die communication, because it's a different material being used. It's a different technology used to build the vias through silicon vias to communicate between the chips. So each of these are like a topic by itself, which needs a detailed study or research topic and very high in demand in the industry today. I'm just giving a overall glimpse how the industry is moving for you to get a little insight. But yeah, each topic has a lot of research being done. Okay, so just a quick overview of why 3D package is needed. Why can't we live with the single simple packages? As you know, chip sizes are getting bigger. I just said, right? The GPUs needs billions of transistor in a single chip. Now, if you make all the transistor in a single chip, the chip is going to be huge. Now, there are multiple kind of component in the chip. Some are the analog IPs, some are the digital IPs, and some are the memory component like the E-flash or DRAM and all that, right? So there is a specific node which is apt for a specific IP. For example, analog IPs we need very stable process, because a small variation in process will change the performance, and the performance of the chip will be not be acceptable. So we need the IPs to be built on a particular process, tested thoroughly on a test chip, and then we use it for years, like not just for 1 or 2 years, like 5 years, 10 years. So we don't change it every time a new technology nodes are introduced. The flash and DRAM technology are typically ahead of the logic technology. They are much ahead because the bit cells needs to be very small and very well packed for keeping the area and power efficient. So these are typically much ahead in terms of technology and work on a different technology node. The logic, like the gates and all the algorithms, everything, we need very high speed and we need them to be very low power. So this is the logic which needs to be on the latest tech node, as we just talked about 3 nanometer or 2 nanometer. So we cannot keep them on the same die uh, if we have a single die. I mean, we can, otherwise we need to change the IPs to be able to accommodate them. So if we are going with 3D package, each of these could be on a different technology, and that is how most of the chips are bigger chips or complex chips are being designed, like GPUs or even CPUs. They have a completely different chip for memory. They have completely different chip for analog IPs and logic. And even for logic, there will be multiple chips. Okay? This also enables reuse of IP across generation of product, because designing the IP is a very complex and expensive job, and also it takes years to stabilize them. We don't want to change it every couple of years, and this reduces the cost as well as time to market. Okay. So a typical chiplet will have a memory die, compute die, and IO die. IO die is where we have analog IP like SerDes or PLLs and other things like that. Okay. So as I just mentioned, right? So each die, when they are manufactured in wafer, they will be coming out from different wafers. First, they will go through their wafer testing individually, and when they are combined in a package, then at a package level, we need to again test them as a system, and again as a chip integrated system, integrated package chip. The interface between them has to be tested, you know. So again, there are multiple pins which are going out, and through those pins only we have to access the whole chip, multiple chips. So that adds a extra layer of complexity. Okay. And how the 3D packages are done, a quick overview, that there are multiple chips and there are through silicon vias which goes from one chip to another chip. And as I was mentioning, these are different kind of material. These are not like the silicon vias which connects one metal to another metal in a chip. These are very specialized technology and very sensitive. And as part of testing, we have to ensure there is no open short, there is no extra parasitics, delays in these micro bumps or TSV, right? So yeah, so that is another area of testing which gets open up when we go to 3D packages. Okay, so overall, what are the challenges? The power is the biggest challenge today. So these are in the order of importance in the industry. You know that the NVIDIA Blackwell, just an example, right? The AI chips are consuming a lot of power. You must have heard about it, read about it, that in 2030, the whole the data center will consume 8% of US power. So data centers today, the new data centers which are being planned have nuclear power plant associated with them because they need huge amount of power. For example, this Blackwell 320 B200 GPU, it consumes 1.2 kilowatt. It's almost like running an AC, right? So power is very critical, and more and more innovation happening in lower power chip. Even in testing, it is ensured that any chip which is going to customer should not cross a particular power. So as part of the screening, power testing is mandatory. Speed, we need more computation, especially with AI. There is a lot of computation involved, which needs high speed to be able to perform higher number of operation per second. And just shrinking technology is not helping anymore on reducing the uh, area or increasing the speed. So this becomes another challenge, and that's where we are looking at multiple dies. So we divide the CPUs in different dies and work parallelly to achieve the same performance. The yield, the lower yield and low tech node due to the shrinking geometries, because of the small gate length and the variation is across us, the wafer is very high. um, the small geometries is yield, resulting in a lower yield. Like in 5 nanometer, we have reached to around 80% after several year of process improvement, and 3 nanometer we are still at 65%, which is in production since last 2 3 years. And we may not be able to achieve 90% or 95%, which we were able to achieve on say 28 nanometer. So these challenges will we have to deal with. And again, testing is a very critical task here, because when the faults are so high, resulting in such a low yield, we are not sure whether we are actually testing all the faults. This is yield based on the faults we are able to test, and make sure that the chip is good. But still, there are certain faults which might not be tested and which will occur at customer field, and those will result in a customer return. We need to debug and find out what was the issue, what fault model was missed in our testing, and develop that fault model and use it for next set of chips. So this is a continuous process. And the cost is definitely a very important factor. To give a flavor of it, the mask cost for say 90 nanometer is in the range of few hundred k dollar, less than 500 k dollar. But mask cost for 3 nanometer is around $10 million. So this is just the mask cost. The wafer cost itself is also having similar variation. So the cost of the chips are increasing very rapidly because of the equipment cost, because of the complexity and all the factors. But the fact is, in industry, the chips are still sold at a very, very low cost. Forget about the GPUs, which are currently in high in demand, but the other chips are sold at a very low cost. So it makes it very challenging for the chip designing companies to find a balance between the cost and the profit. So it's a really tough challenge, and the companies are solving in multiple ways. Okay, So what is the path forward? Continuous innovation in low power technologies by changing the geometries and technologies, finding like we move from planar to FinFET and gate all around, and more innovations are happening. The logic design itself, we design the chip in such a way that power is not consumed when not needed. For example, adding enough clock gating. I mean, these are very, very basic things which we are have been doing since decades, but doing more fine-tuned gating and intelligent gating, or cutting down the power of a specific logic when it is not in use, power islands, you know. So that is under implementation. Using lower leakage cell instead of higher leakage cell in implementation is still meet timing. So those are day-to-day challenges every company is facing. Other is move from cloud AI to edge AI. As we just talked about, cloud AI is the talk of the town today. Every company is moving to AI and they are taking a lot of server space which will run on cloud. But cloud AI takes a lot of power because it needs to process huge amount of data for learning as well as for inference. All the data first need to be transferred to the server and then send it back to the client. That's not efficient, and that is the reason industry is moving toward edge AI, where most of the processing and inference happens at the edge or at the end device rather than every data goes to the cloud server and come back. That is very power efficient and very fast, and that adoption is happening very rapidly. Even hardware is also having the product in this direction. Our solutions will all our solution will have edge AI to make sure we have intelligence in the chips as well as we also have the power efficiency. Okay, and then more and more chiplets instead of the single die to have better yield and better reuse of the IPs. Okay. Okay. So this I will move to the testing. Any question till this point? Okay. So there are multiple type of testing and done at a different levels. I will give overview of all of those, and some of them I will get little deeper, which is the being used in the industry. I mean, due to lack of time, I cannot cover all the topics in detail. But in future presentation, I would like to do that if I get an opportunity. Okay, so again, I think this part you might already be aware how in the whole SOC design flow testing takes part. So after we go from specification to architecture, RTL design, which is the IP design, and synthesize the RTL, we insert the DFT logic. And what are those DFT logic? We will see in the coming slide, and you might also be aware of various type of testing we do. So for each of them, we need to insert the logic here. And once it is implemented through all the flow and chip is out of fabrication, that chip is tested. And this is another area where test is critical. So in the whole flow, these are the two areas where the focus is, but testing is considered at every step in the flow. So the engineers who are doing testing, we call them DFT engineers, they are engaged in the chip design from day one, starting from specification till the chip is out for the production. There are various other engineers who will have very limited job in the whole flow, but testing engineers job doesn't stop till the chip is in the in the market. Even after that, if there are customer returns or yield fallout, test engineer has to be back in the job. So this is one of the most interesting and complex area of the chip designing. Some of the facts of silicon testing. So testing can be broadly categorized in two parts. One is the functional testing. Like I have designed a chip and it is supposed to do a specific function. If there is a function is not being performed, that means customer cannot use it. This is done on a few samples, not every chip, because this will not, there will be issues in this kind of issues if there is an issue in the design. Like if my logic is not designed correctly, there is a corner case where logic is not performing as expected. So those kind of issues might be there in the chip, which I would have not been able to catch during my pre-silicon simulation. So that I need to catch in the silicon, because silicon is definitely running at a full speed while my simulations are very slow. I cannot cover all the possible combinations. Here I run the software also on the chip, so all the practical applications are run and those are caught. So this is done on a very few sample chips, but manufacturing does testing is done on every chip because each chip is different. Each chip, uh, due to process variation, there could be faults, and by testing few chip, I cannot ensure the rest of the chip in the wafers are good. Okay, and this is the area where a lot of innovations happen. A lot of because we need to reduce the cost of testing. So area of test logic, as we just said, right? There is a logic insertion in the design flow. This is in a typical SoC, it is 5 to 15%, but I have seen the chips where it is 30% also, depending on what kind of testing is more in a specific. If there are a lot of memories, it will have more overhead. If it is more of a digital chip, it will be less overhead because memory based needs a lot of logic, right? And as we go forward, the number of algorithms added to test is even more, so that increases the test logic area. And cost of testing a chip, it could be anywhere from 10% to 30% of the overall chip cost. So even the area itself is a cost, and over and above test testing of the chip, which takes the tester time, is also a cost. So overall, if you see, it is a significant portion of the chip cost. And this is the area where companies want to minimize, because this is not practically adding any value to the customer. By default, a customer is expecting a functional chip with a lot of feature. So customer doesn't care how much we are testing because that is the default expectation. This is to ensure our chip is bug free. So there's a lot of focus in the industry to optimize this cost. And companies are working, EDA companies especially are working on this day and night to bring new algorithm, new methods to support the bigger chips as well as optimize the cost. Okay. So as we just talked about, right, why each and every chip needs to be tested. So just to give a little more data on that, right? So this is a wafer, and there could be hundreds or thousands of chips depending on the size of the chips. Typically, we have 8-inch wafer and 12-inch wafer. In older technology, we have used to have 8-inch fabs. They used to build 8-inch wafer. Nowadays, all wafers are 12-inch in the new technologies. So while fabrication is happening, there are various reason the characteristic of one chip will be different from other, because during overall in the wafer itself there will be variation in terms of gate length, metal resistance, doping, etc. Even some of them might be completely different from the other. If you typically in the center of the die, center of the wafer, you get the best die, and toward the corner you get the worst dies. So it is that is the reason it is critical that we test each and every chip, because we need to achieve very tough ppm goal, parts per million. This is a terminology used for the failures seen by the customer in the field. Especially in the automotive industry, the norms are very high, because even a single failure can be catastrophic. So there are completely different standard for automotive to comply with the automotive test standard. And due to that reason, typically automotive chips are on a older technology node, which are more robust and proven, and volume production has been done over several years. Okay, any question up till now? Okay, so what are the type of manufacturing tests, which is my focus area today? So digital logic, which is like standard cell and or logic gates or all kind of gates, flip flop, all this is tested by scan, or we call it ATPG, automatic test pattern generation. Okay, then memories are tested with MBIST. Then there are IPs like analog IPs like SerDes, PLL, IO, sorry, SerDes, PLL, or maybe uh, analog to digital converters. So those cannot be tested with any of these techniques. They need functional tests. We need to really uh, apply the functional scenario on those and see the outputs and measure the voltage as if it is meeting the required criteria. So typically these are a little more complex in testing. More than the complex, it is more test time consume. They take more test time and costly in terms of overall factor in terms of total cost. Then IOs, all the IOs needs to be tested. Like the external device is out of our chip has a specific voltage level defined. Like for example, this IO I have defined this is going to operate at 3.3 volt. Then there is a range in which it has to operate. And when we sell this chip to customer, we have to make sure that the specs are meeting those criteria. It should be within that range. So for each IO, we have some specific tests which are done through boundary scan. Okay, so these are the major category of the manufacturing test. Okay, going further in the details into the scan testing. Okay. So scan testing, I think you might already be aware of. So in scan testing, there are additional mux is added with each flop, and all those flops are stitched in the scan chains. So each flop will have two input. One is data input, other one is scan data input. And through scan data input, they will be connected with each other without any logic. Now, cost of scan testing dependent on the length of the scan chain, because first, as a step, the data has to be shifted in, and the number of cycle or time needed to shift data will depend on the scan chain length. Okay, this is the fact I think most of us must be aware. And the coverage target are typically 99 plus, and rather nowadays it is being pushed to 99.7% also. Okay, so these are the basic of scan testing, and with this we test all the flip-flop combination logic for all kind of faults, stuck at 0, stuck at 1, and delay faults. So this is the most popular technique being used over years for digital logic. So as I just mentioned, all the flops are connected in scan chain. There will be multiple chains depending on how many pins you can give for scan in and scan out. You can create as many chains. Suppose I have 20 pins available, then I can have few pins for scan control and then rest of the pin for scan chain, say 16 pin for scan chain. So 8 chains I will have. If I have say 10,000 flop or 12,000 flop, I will have approximately 1,200 flop in one chain. So that becomes the chain length, and that will determine the cost of scan testing. And not just it impacts the test time, also it impacts the memory, tester memory. So when we do the design and test the chip, before that we need to generate a lot of scan patterns, vectors, and upload it to the AT tester, the automatic test equipment which tests the chips. Now they have some limited memory where they need to accommodate all kind of tests, scan test, MBIS test, function test, for analog IO or IO test, everything. So if my scan chain becomes long, for each, the number of shift I need to do is more, and then each pattern, each vector will take more number of steps, and memory requirement will be high. So sometimes I am not able to fit all the vectors in the tester memory, or I need to enhance the memory, which cost money. Okay, so this is the traditional technique which was used, maybe I would say 20 years ago, where we will have direct scan chains, and the reason was the number of flops were very limited, and we were able to accommodate them even with the 1,000 scan chain length and all. Okay, but as I mentioned, the pros are, it's a simple implementation, minimum logic overhead. The only logic overhead here is the scan mux before each flop. That's all. And they are very simple to debug. If on silicon a pattern fails, I can directly locate where, which flop it is related to. Suppose I get a failure on fifth cycle, I can go back and check what is my fifth flop and what is the associated combination logic. So it is very straightforward to debug. But what are the downside? As I just mentioned, long scan chain leads to high test time, high test memory, and overall high test cost. And focus is always to reduce the cost. So this was okay 20 years ago for smaller chips, but as we move to the bigger chips, it became very painful because the flop counts were increasing exponentially due to design complexity, the computation we are doing in the chips, and scan chain length was increasing. Both tester memory and test time increased multifold, and this makes the traditional scan unviable. So EDA companies like Synopsys, Mentor Graphics at that time, they were working day and night to find a solution. And then they came up with the solution, compression. This was a big relief for the industry. In this case, the chains are compressed in few channels. For example, there are 10 chains, and those chains can be compressed. And at the chip level, we just need one channel. So I'm shifting data only on this line and shifting out data on this line, but internally it is relaying to multiple chains. So there are some logic implemented for the decompressor and compressor to ensure all the faults are tested properly, all the data is captured properly. So this is like a proprietary logic these companies have developed. Both the companies, even the Cadence is a third company, all of them have their own technique. They are largely based on compression, but exact logic implementation is different from each other, and they're all proprietary. But the results is same. We can now compress the chains up to 1,000 or even more. So the compression ratio which I have achieved in my few past projects is up to 1,000. So 1,000 chains can talk to single chain. That's a huge saving in the test time as well as the tester memory, and reduces the testing cost significantly. Like it keep it to the fraction of the overall cost. Okay. So what is the methodology here? The scan data comes in and it is exposed to multiple chains. So the tools are smart enough to know which data they want to send to which flop, and accordingly they push the data. And then there will be some logic to ensure all the flops are taken care. In some pattern, only few chains are taken care. In some pattern, other chains are taken care. So that is a very complex algorithm. But ultimately, the goal is achieved with a much smaller number of patterns and overall test time. Okay. So here I'm showing one channel and two scan chain, but it could be like 1,000 chains here and maybe two channels or five channels here. It could be any combination. It depends on how many flops I have and how many input output pins I have for scan in the chip. Even further, when we started with compression, it was good in the beginning because I was able to reduce test time, but it showed me a lot of challenges in the implementation because there is a compressor logic which sits, it's a very small logic which will be talking to scan in and scan out. But from that compression logic, there will be so many chains going out. So this routing the signals from one small compression logic to the across the chip was very painful. It will take a lot of routing resources as well as a lot of buffering needs to be done. So soon it became unviable to have single compression engine. So then the new approach came, which is modular approach. What it means is in my chip, I just don't need to have only single compression engine. I can have a compression engine in each block. Suppose my chip has 10 sub-modules. Each sub-module can have its own compression engine. And I will have few scan channels dedicated for each block. Okay, so I just showed one channel for each, but it could be multiple channels, and even the number of chains could be different. Here I can have 500 chain compression ratio, like 500 1,000 chain and two channels. Here I can have only maybe say 200 compression ratio. So depending on multiple factors, I will decide what is the compression ratio for each block. But typically, what we try to do is we try to keep the chain length same across all the blocks because the test cost or the pattern size will depend on the highest chain length. Even if one chain is suppose all most of my chains are 50 flop, but if one chain is 70 flop, the tool will still have those extra 20 cycle for each pattern. So then I am not effectively saving the test time. Okay, so typically they are very well balanced, and they are to ensure the smaller vector size and the test time. Okay, so with this approach, it became very simple, and this is still, I would say, the most popular technique for scan being used in the industry today for most of the chips. But again, as we are moving forward, more challenges are coming. So, so the good part is it reduces the cost, but with compression, if you compare with the traditional technique, there is a overhead of compression logic. So this is an increased logic overhead which cost area, and complexity of debug is also very high because if there is a failure, I don't know which chain it belongs to. So again, tool vendors have done a phenomenal job of creating algorithms to help you to map it to this failing flop, but it is sometime only very few time it is accurate. Most of the time it just give you the some hint, and we need to put some effort to find out the exact fault. So this has been a challenge with the compression technology, but it's still very useful and most popular technique today. And again, tool vendors are continuously working on improving their debug capabilities. Okay. Any questions so far? Okay. Okay. So we talked about the test time and test memory and the cost related factors, but there is also another factor which is implementation challenge. As you know, we put all the flops in scan chain. These flops, you see, there is a connection from one flop to another flop without any logic. Okay. So unless I balance these clock of these flop very well, there is a possibility of hold violation here. So it is very critical for any design that clocks for all the flops are very well balanced, especially in the lower technology node. There is an on-chip variation where um, even within a die, we assume, I mean, there is a process variation, process temperature and voltage variation that needs to be accommodated by putting some derates or adding some pessimism. So with all that, this path will have violation, timing violation, mostly hold violation, and this needs to be very well taken care, because if there is a hold violation here at chip, I cannot test that chip for scan. So these are very critical timing checks. Okay. So to ensure there is no hold violation, I need to balance all the clocks. And balancing the clocks for all the flop in the chip, or even for few chains, it's not easy. It takes a lot of efforts, a lot of area and power and routing resources to be able to achieve that. For smaller chips, it is fine. For smaller block, it is fine. But for increased chip size, it is practically impossible to do it. For functional logic, functionality, we have solutions where we don't balance the clocks from one functionality to another functionality. We use synchronizer so that it eases the pressure on the clock tree balancing. But in scan, that is still a challenge. Okay, so just to give an example, right? If my chip size is small, this is my scan clock input. If there is a flop sitting here, this clock needs to be routed to this signal. Now the routing delay itself is very high, and if you want to match the latency, I need to add a buffer to match the delay between these two. Now again, if this flop is sitting very far, I need to put extra buffer for maintaining the transition. And if I'm adding extra buffer here, I again need to replicate the buffers here to balance the delay between them. So it becomes very complex and difficult. Over and above, there is an on-chip variation factors, pessimism factors applied, which makes it even difficult for timing closure. So for small chip, the challenge is less, but when chip become bigger, the challenge is even more, because now I need to add more buffers here to balance the net delay. And again, net delays and cell delays varies differently on silicon, because their processes, this is more of a resistance based, and this includes the active devices and as well as resistance, right? So the response is different with the process variation. So across process, voltage and temperature, balancing them is a nightmare. Okay. So one is the we have to add a lot of buffers, put the even the whole buffers between them from one flop to another flop, and there will be a lot of routing resources which will be consumed. So overall, there this becomes compression technique also is effective to a certain extent. Once we go to chips like GPUs, or any chip like beyond 100 square mm, 200 square mm, this is practically not possible to use this technique. So the other technique which came into picture a few years ago is packet bit transfer. Scan testing uses packet based transfer, and Mentor Graphics, which is now Siemens, came up with this technology for the as a first mover. And I've shared the link here, which has more details. So in this technology, data is not just shifted to the flop directly or through a compressor. It gets into the chip in terms of packets, and now because it is shifted as packets, it doesn't care about the uh, much of the data shift from the previous stage to next stage, the timing between them. I'll show more details in the next slide. The advantage of this is it makes the design modular. You it doesn't depend how what is my overall size of the chip. What I care about is what is the size of my block. As long as I'm keeping it limited within the range, I'm able to support it very well with the very simple implementation. And it offers further test time reduction. And as I just mentioned, Siemens has this technology in their scan testing tool with the name Streaming Scan Network (SSN). Okay, so this is the high-level overview. Again, I borrowed it from Siemens. How the SSN network look like. For example, there are 4 or 5 blocks here, 4 blocks. So what we were doing earlier, this EDT logic, which is called compression. EDT is a Mentor Graphics or Siemens term, but it is a compression logic. We were pushing certain scan in and scan out directly here for each. Okay. But now in this technology, this does not talk to the pads directly. There is a bus called SSN bus. This is the bus used for shifting the data in and shift the data out. And it does not depend how many channels this compression engine needs, how many chains this block has, or what is the compression ratio. It all, I mean, it is not limited by all those factors. This technology, this technique works in any kind of design and very modular and customizable. Okay, so in this method, the data is moved in the packets, and each of this SHH engine, which is the main, I would say, heart of this technology, will intercept that packet and absorb it according to the address it has. Okay, so we'll talk about it in more detail in the next slide. Along with the traditional logic, which have like compression logic, we also have a JTAG, IJTAG logic here, which is used to program these SSH engines. Okay, so this is a configuration path, and this is my data path for testing. Okay, so SSH is an interface between SSN bus, JTAG, and compressor logic. Okay, and this controls the whole scan operation for this particular block, and also talk to the talk with the outside world. Okay, IJTAG, it is used to configure the SSH. This each block will have an IJTAG, and it will define the characteristic of this SSH, and accordingly it should match with the packet characteristics so that it can operate as expected. Okay, and EDT and compressor, this is all we just talked about. This is the same as earlier. For this block, all the chains will be compressed and talk to EDT, which is a compressor. Okay, so let's talk about SSH. What is SSH? It intercepts the packetized scan data from SSN bus. Whatever data was coming in, it will first intercept it, and the packet size is actually total number of bits needed by the whole system. So for example, block 1, here we have 5 channels, here we have 2 channels, and we have one channel here. So 5 plus 2 plus 1 plus 1. 9 channels are there in total. Channel means number of scan in and scan out talking to EDT or compressor logic. So suppose there are 9 channels in total. So in that case, the packet size will be 9. So 9 signals will come here. Now SSH knows what is the, out of those 9, which data it has to keep, and rest of the data it will transfer it to the next node. These are all called nodes. So that is how it works. and SSH plays a critical role here. So first it intercepts the data, then it keeps the data which is intended for it and passes it to compressor. Passes it to compressor here. Then each SSN is a unique location and ID. Like depending on where it is located in the whole chain, it will given a unique ID, and IJ tag is used to configure that ID, and based on the ID it knows which data it needs to keep and which data it needs to pass it forward. Okay. Okay, what is IJTAG? IJTAG is a single bit JTAG interface. Typically, it is a 5-bit interface. Here we are using a single bit. This is used for configuring the SSH, as I just mentioned, right? So SSH, certain characteristics needs to be defined. A location in the series of node, whether it is first location, third location, fifth location, because it needs to intercept those packets, those bits in the packet. It also configures the number of shift cycle and scan enable transition timing information. When exactly the scan enable is toggling from 0 to 1 and 1 to 0. Okay. So before we do the actual operation of scan testing, IGTag is used to configure all the SSNs, and then the actual testing starts. Okay, so let's look at the whole operation. First phase is a setup phase where each node is loaded with the information related to protocol. So it will have active bus width, node location in the series of node driven, the number of shift cycle per scan pattern, and a scan enable transitioning information. This is what we just talked about. Then scan in phase will come where data is shifted, entire pattern set is applied in the packetized scan data. So the data will push on the SSN bus, and then it will reach to the all the SSH IPs.
Excuse me, Deepak sir.
Yeah.
Sorry for the interruption. Should we take a 5-minute break or is it okay to continue?
Yeah, we can take 5-minute break. That's fine.
Okay, sir. Okay.
Sure. I'll come at 12:16. Okay.
Okay, sir. Okay. Deepak sir. Hello, Deepak sir. Deepak sir, are you there?
Hey, hi. Can we get started?
Sir, there are a couple of questions in the chat box from.
Okay. Okay, let me see. Chat box. Okay. Okay, in 2004 is 40 nanometer. Why it increased to 65 nanometer? I think it might be a typo. It's not. So let me give you one uh, fact, right? So different foundries work in different step. Not every foundry work on each node. For example, TSMC, they had 28 nanometer and they went to 16, while they skipped one of the node in the between, while other company like Intel, they worked on 22 nanometer. So yeah, this might be very, it might be a typo or something, but just want to give you the fact that every company has a set of node which they skip because it's not possible for them to spend or invest on each technology node. Okay. Edge AI. So, okay, I think the question is what is Edge AI? So, I think you must be having the basic understanding of AI where the data is used to train the models first, and then based on the inputs, we use the trained model to provide the output, right? Which is called inference. So currently, wherever most of the place where we are using AI, first the first step is data is trained, and the servers are trained, the models are trained with a lot of data. For example, OpenAI is doing, Microsoft is doing, they have their own model, they have data available from various sources, they are training it, and those trained models are available on the servers. When we want to use that for inference, so any input has to go on those servers, and those server will use those model to generate the outcome, and then outcome will be sent from server to your device. The device could be your phone, it could be your laptop. Suppose you're asking a question on your laptop, your or on your phone, it goes to server and comes back. While in Edge AI, the inference, which is the answering part, can happen in your device itself. So how it works is the training happens in the server, and then some of the smaller set of models are moved to the edge device, which is your phone, laptop, or any other device which is close to the customer use or end use case. And then, in case of any event or any question asked or any requirement, the answer is given immediately on from that. Processing is done at the device itself. It doesn't need to go to server. So that is edge AI. So there are small. So currently the models for AI are very heavy. They are like billions of parameters. But for edge AI, the companies are coming with the lightweight models. The number of parameters are less, and they are very very targeted to a specific application. So it will not have all kind of information processed. So these are very focused models, and that is the reason they have been able to accommodate on the device itself. So a lot of work is going on in this direction now. Hope it answers your question. Okay. So yield decreases as decreases, so time to test and repair would increase. Also, what if we have already achieved lowest node possible? Yeah, so yield decreases as node decreases. Right, that is correct, because the geometries are so small that probability of manufacturing fault is high. Even a small variation in doping, small variation in the metal width or via anything can cause a failure. So that is the reason yields are decreasing. And why the test time is increasing, because we should be able to discover all of such faults. So newer technologies are needed, deeper analysis are needed. I mean, the next point is, what if we have already achieved the lowest node possible? That has already always been a debate. When I remember when we were 10 nanometer, there were talks about, we cannot go further. Only multi-die is the only option. But then 5 nanometer came. Then 5 nanometer was supposed to be the last node, but then we got gate all around technology. Now companies are working on one Armstrong or even below nodes. So I mean, I would say until we discover something, it is always said to be last node. But yeah, there is definitely the gain is not significant from technology to technology anymore. It's only incremental, and that is the reason there's a lot of focus on quantum, where it is a leap, in terms of changes in terms of leap, right? So that is a completely different topic, but yeah, until now I think this will stay, and this will still, there'll be a lot of innovation keep happening in this area, semiconductor area, and I think we will still milk this technology for a few more decades. Oh, where is the role of layout engineer in SoC design flow? So layout engineer, okay, let me share my screen, and I think I should be able to. So after, while the screen is coming up, when the first step is the logic design, where the RTL is developed, and then it is synthesized. Synthesized means it is, the logic is mapped to the standard cells. Okay, so there are logic will be mapped to the AND gate, OR gate, flop, inverter, and whatsoever. Once that happens, the place and route happens. Means we need to place that logic in the real silicon, right? So that is where the layout engineer role start. Nowadays, even the synthesis is layout driven. Like during mapping of logic to the gate itself, um, we give the constraint to the tool that this is the total area available and this is where you need to place it. So the synthesis does better optimization in terms of area and power. Are you able to see my screen? Hello? Hello? Anyone can answer? Are you able to see my screen?
Yes, sir, it is visible.
Okay, okay. So, yeah, so basically what I was telling is, yeah, so this is the area, this is the point where the layout engineer work start, floor plan. So it will, layout engineer will define what is the total die size, X and Y of the die, IO placement, and then placement of the logic, clock tree, routing, and all the check all the DRC rule as per the foundry are met or not, right? So this is a layout engineer's span. Even the timing is there, right? I have not mentioned here, but parallelly we have to also make sure the timing is met. The frequency for which we are targeting the chip, it should meet that frequency. So those checks are also done in parallel. Okay, yeah. Hope it answers your question. Otherwise, feel free to ask me. Going back to the more questions. Would we need to cover more than just all stuck-at and transition fault in testing? So there are more models. So okay, so stuck-at is a basic model which is very old and it is definitely mandatory. Then the transition fault testing is done to ensure we meet the timing or it meets the frequency. But there are more models like a path delay model. So though transition fault testing is meant for checking the speed of the nodes, but if we really go into details, you will find that transition fault testing does not ensure that chip will meet its frequency because it may not be looking at the worst path in the design. So there are, I mean, again, it's a pretty detailed topic and needs its own hour. But when there are multiple nodes in a path, they can take any path, and the path taken by transition fault testing could be smaller than the worst path. So in that case, it does not ensure it is meeting the frequency. So to ensure the chip meets the frequency, there is a different path, different fault model called path delay model. The path delay model, in this case, what we do is we take the worst path in the chip. Worst path means the timing path which is having minimum margin. Like for example, if your period is 1 nanosecond clock period, and that path is taking say 0.99 nanosecond or 0.999 nanosecond, right? So that means that path is just met. If we meet that delay, that means chip is good and it is meeting the frequency. So such paths are dumped from the timing tool and spatial patterns are generated to test that. So that is one thing. Again, it's a variation of transition fault, and then there is a small delay defect, again a variation of transition fault. These are advanced technologies. Then there is a bridging faults. Like if there are two nets running in parallel, there could be coupling effect. So the bridging faults are also important because they may not occur while we are doing the stuck at a transition fault testing, but they may occur when both the nets are toggled together. So yeah, these are the additional faults we have been using in the industry for scan testing. This is just again for digital logic. Okay. Okay, what skills are required to work on edge AI? So again, AI is have a multifold impact, right? So one is there is a chips which needs to be designed to work for edge AI. I mean, there has to be algorithms added for edge AI algorithm needs to be added into the chips. And then the other part is the software where the AI libraries needs to be developed default the model needs to be developed for edge AI. The lightweight model has to be developed. So both in software and hardware there is a scope, but it is not different than the traditional AI in terms of skill. I would say same skill will be applied here. Just we need to shrink it to be able to make it lightweight. Okay. Okay. So Sai Kumar, there's a question which is not answered. Okay. Okay. Any other question before I move to the presentation? Okay. So I think we were here. We were talking about the SSN. Okay. Okay, operation of SSN, right? So we talked about the setup phase where through IJTech each node is configured. Then we do the scan in, shift in the data, and each node will intercept data meant for it and pass on rest of the data to the next node. And after that scan operation phase here, each node will push the data to the compression engine, do the scan testing, and capture the scan outputs within the node. And then scan out phase where all the nodes will push out their captured value to the SSN bus. Okay, so this is kind of a 4-phase operation which happens in the SSN based architecture. So what are the advantage and disadvantage of SSN based testing? This is scalable design. It does not depend how many scan pins you have, how many flops you have in the design. This technique will work in any complexity, simple chip, small chip to the biggest chip. So this is very scalable technique. In design, and it is very friendly to design implementation because we don't need to balance clock across the chip. We just need to take care of specific nodes. Within the nodes, they need to be balanced, and then again the size of the nodes we can decide, which is convenient for physical design purpose. So this reduces the overhead of routing, clock tree balancing, clock tree buffer significantly. And this is the only way we can really achieve scan testing in the big chips. The traditional techniques will increase the area of overhead significantly and definitely reduce cost because we will be able to have less area for the clock tree buffer, less number of wires, reducing the routing overhead. And what is the downside? It has increased logic overhead. As you have seen, each SSN as node, each node have its own logic. IJTech has its own logic, which needs to be added. So there is little cost of that area and increased debug complexity because now it is a packet based. Another layer of debug is needed beyond compression to find out where the fault has occurred. Okay. Okay, so I just try to capture here how the different technologies are being used across the nodes. Traditional was used till maybe I would say 20 years ago. Then compression was used and it is still being used today. But the SSN based testing was incorporated or introduced maybe around 5 years ago or 7 years ago. Okay. So now switching to the memory yield challenges and solution. So memory testing is a completely different way of testing the as compared to the digital logic because memory has a lot of bit cells, and we need to ensure each bit cell is tested. Now we cannot add separate test logic for each bit cell. It's a very small bit cell, and we cannot add any logic there. So the way we do is we test each and every bit. We read and write in each bit and make sure the results are matching what we expected. And there are different kind of fault model. I think as part of this uh, conference also there are some papers presented on that. So depending on the technology, there are different fault models used to cover all kind of faults. And sorry, here is a typo here. Okay, so this MBIS logic is nothing but a pattern generator. It generates some random pattern based on the algorithm, and it pushes the data on the memory bit. First write it and then read it back and compare. So this MBIS engine, one MBIS engine can take care of multiple memories, and there could be multiple MBIS engine in a chip. Now this MBIS engine has some logic, and that is the area overhead we come across when we use this testing method. But there is no alternate option as of today for memories. So I think I'll not go into detail of memory-based testing or the algorithms. I'll touch upon what are the challenges with memory. So memory yield is a big challenge today because if you remember in the beginning, I told memory technology is quite ahead of standard cell technology. The bit cells needs to be very small and very compact, and that is the reason the probability of fault is also high in memory as compared to the digital logic. So that is one thing. The other thing is the number of memory bits in a design or in a chip has increased exponentially because there's a lot of algorithm, a lot of processing of data happening in the chip, which needs intermediate data to be stored, which happens in the SRAMs. So with the increased number of bit cell, even the probability of getting a failure also increases. Okay, so therefore it becomes very important that we first of all we test every bit properly so that there is no faulty bit remaining in the device which goes to customer. And once we find a faulty bit, how do we still use a die? Because just because few bits are bad in this whole memory, I don't want to throw away the device. That if I do that, the yield impact is will be very high. I mean, if I talk about the technology like even 90 nanometer, which is very old, uh, if there is about 1 million bits in a chip, there will be around 10% chips which will be having memory fault. And nowadays, with the lower nodes, is even 50% or more. So memory faults are very highly probable. And so that's the reason we need a solution where we can repair the memories once we found the fault in that and still use the chip. If we don't do that, then this business will not be profitable. So this memory repair technology has been again in the industry for say almost like 20 years or 15 years, but it has evolved over a period of time, and we'll talk about that. Let us first talk about how memory repair works. So while memories are being developed, there are some spare row or columns added. Some memories will have spare rows, some will have spare column, depending on the foundry and the technology they are working. It's completely their decision. And certain time they will have both spare column and spare rows. Okay. When MBIS testing is done, the faulty bits are identified, whether it is here in this particular row or here in this particular row or column, right? So memory bits will definitely know the location. After MBIS testing done, it will know the locations of the bits which are faulty. and that information is stored in the chip in OTP. OTP is one-time programmable memory. So this is like kind of a fuse box or some kind of a memory where the faulty bit data, that which, if suppose is a redundant, it has a redundant column or spare column. So it will store which columns have the faulty bits, that kind of information here. Okay. And then when functionally we are trying to access that faulty column, the redundant column will be replaced by that. So address of the redundant column will be replaced. Sorry, redundant column will replace that column. So suppose this particular bit is faulty and I'm trying to write that, my repair logic will actually point me to this column. So I will never see that column which has a faulty bit. I will always be, the address of the column will change by the repair logic that I read and write from here. So that is how the whole repair algorithm works. And this saves a lot of dies from being thrown. We are able to save those dies and ship it to customers. So this is very popular technique and we can't survive without it now. So as I just mentioned, right, this technique has also evolved over a period of time. So there was a traditional technique where MBIST was first run and faulty bits are identified. And this information of faulty bit is processed inside the chip. Sorry, I think. Okay, there's a topic. Okay, so in traditional, it is faulty bits identified and the bits are shifted out of the chip. All the faulty bit information is shifted out of the chip. Then repair analysis is done off the chip. So after the data is out, there will be some compute logic, some some server will be doing this computation, that are there enough redundant rows and columns to fix all the faulty bits? And if yes, which rows and column need to be replaced? So that kind of analysis is done. And then that repair information is shifted into the OTP, one-time programmable memory. So then after that, when chip is powered on, it will ensure that anytime a faulty bit is referenced, it will point the address to the redundant address, redundant column. Okay, so this is a traditional technique. While in the automated technique, the data is, first step is same, BIST is run and faulty bit is identified. Then information on faulty bit is processed within the chip. It doesn't need to be shipped out. So there is a logic inside the chip which will be doing the same job. It will first check whether there are enough redundant rows and columns to fix all faulty bits. If yes, then it will identify which rows and columns to be replaced and pass that information into OTP. If no, then it will mark the device is faulty. It cannot be used. Okay. So in this technique, what is the advantage? Advantage is it is very fast as compared to traditional approach, because data is shifting out, processing outside and shifting in. It takes a lot of time and tester time is very costly. So I'm losing a lot of time and overall cost of test and repair becomes high. So definitely this is a preferable technique and which is used nowadays. And the downside is it has a higher logic overhead, because there will be some repair logic needs to be added within the chip. Okay. Okay, I think that's all till memory repair. Any questions on this? Okay. I'll just skim through the other testing, not go into details, deep on those due to time limitation. So, analog IP testing, as we just touched upon in the beginning, behavior of all analog IPs varies with the process, and the impact on the analog IP is much higher than the digital logic, because small variation in doping can change the behavior, the noise level of the signals. So to test them, we insert the specific logic which will generate some test pattern. So some test logic is added here, which will create some traffic to send. This is an example of a SerDes where it will serializer, deserializer. So it will send some data outside. It will convert the parallel to analog, parallel to serial data, and serial data will be shifted out on the analog in the terms of the analog signal outside. And that signal will be checked outside on the tester, or it will be fed back in the same SerDes, and it will be captured here in the test logic and compared whether it is same or not. So this is just one example of how analog IPs are tested. Okay, so IP is characterized sometime there will be variation. So each chip will have a different process variation, right? As we just talked about. So we need to tune certain parameter of the analog IP based on the process of that chip. For example, if the gain of band gap varies with the process, based on the gain in the specific chip, control signals are programmed in the OTP to reduce or increase the gain to bring the same target number. So we observe what is the signal strength or signal gain based on the observation outside, and we already have some control signal which can increase it. So we will hard tie them through the OTP. So anytime the chip is powered on, those control signal will be visible here, and for a specific chip, those values will be used. So again, for each chip, this characterization happens. This again are very expensive. It takes a lot of test time, but that characterization is very important for the analog IPs. Okay, next is the boundary scan. I think I briefly talked about it. We have a JTAG interface, and through JTAG interface, the values are shifted in the IU and observed on the pad, and vice versa. The values are pushed from the IU on the pad and then shifted in the through the IUs and observed here. So this is how the IUs are tested for voltage level and other parameters, electric parameters, and other characteristics. And it also can be used to check connectivity at board between multiple chips. For example, this is one chip, another chip is lying here, and they are connected. It can push the data from here and observe the data here. So it can check whether on the board the connectivity is proper or it is broken. This is another application of boundary scan. Okay, so this is till now whatever we talked about was manufacturing test, and it is tested. It is done for each chip. Now, in the beginning, I talked about functional validation, which is used to verify the functionality of the chip, and this is done on few chip from engineering wafer, early wafers. Validation to complete this testing, some validation boards are designed, and these boards are similar to customer application boards, where we will put the other chips and push even the sometime load the software and transfer the data as if we are doing it in the customer application. And we run it for a long time to check all corner cases. And analog testing, so detailed testing of analog IPs are done because there is a lot of parameters which needs to be tested and checked across multiple wafers, whether they are within the limit. Okay. So we just talked about it, right? Manufacturing test is done typically at two places. Wafer sort. So when wafer arrives from the foundry, on the bare wafer is tested. Each chip in the wafer is tested, and then after testing, they mark which die is good and which die is bad. So good dies are packaged, bad dies are thrown away, and those packaged dies are tested again on the final test. Why they are tested again? Because earlier they were just the silicon. Now here we are testing die plus package, both silicon and package both. That is one reason. Other reason is here we are testing the chip mostly on the room temperature, but here we are testing it at a extreme temperature also, minus 40 degree and also 125 degree junction temperature. We cannot do that here. Okay. So how does wafer testing look like, right? So the wafers, there is a tester head which will have certain pins. This is like a wafer map. So first the wafer is put in, the tester head will come and it will, on each die, it will place certain probes and push the values on for these vectors and check the die, and then it will keep on moving. First it might check this die, then this die, then this die, one die at a time, or it may also do two die at a time or four die at a time. It depends on the how the tester probe size is designed. So it will keep on moving and test the all number of dies. So this kind of wafer map will be visible, which will show which dies are good and which are bad, and bad dies are discarded. Also at tester, what we do is we add some critical information like die identification number, secure key, some kind of a lot number in the each die, each chip for further reference. Suppose this chip fails in the customer field or this chip fails in the package test, we should be able to track it back. Which wafer it came from, which lot it came from, was there a problem in this particular manufacturing lot, right? So unique ID is given to each chip. Then package part testing, once the parts are packaged, those are tested at minus 40, 125C junction temperature. Junction temperature means it is the PN junction temperature, but the ambient temperature outside package, the temperature could be say 85C. So because there is a heat dissipation is not very smooth within the package, there will be temperature difference between outside the package and inside temperature, inside package temperature. Also, the memory repair is performed if there is a failure found related to memory, and characterization of analog IP is also done at both the temperature. So we want to see the all the corner cases. Okay, so this is all about the testing, but in between we have talked about multiple time about the debug also. So suppose a silicon fails, one part is we can just throw the die and move to the next chip. But if the other part is we also need to debug, okay, why a particular chip has failed. Was it a vector issue? What was it a manufacturing issue? Was it some other issue? Okay, so we need to debug the failure. So first the failure log is dumped by at the tester, and then EDA tools have capability where they can provide the suspected location of the faulty gate or flop, and then there are additional testing method which will confirm whether suspect is correct. The other thing is if we don't find any suspect or our theory does not go well, then there are other method to debug silicon. We do it physically through failure analysis technique. And there are many failure analysis technique. And these are very, very sophisticated techniques, required expensive machines, as well as a lot of knowledge about process, not just about the chip design. So there are microprobes where microprobes are like kind of needles which will go and touch the gates inside the chip, or not exactly the gates but the wires inside the chip. So they will check on each specific wire we want to check. It will check whether it is 1 or 0. Emission microscopy is a laser based technique where it will send some ion beam, and then based on the reflected ion beam we will know whether the value on that gate is 1 or 0. And voltage contrast, again, it will check the difference in the, whether it's a different I would say the heat dissipation heat map is different for 1 or 0. So there are quite complex techniques, and it takes a lot of time to really figure out the issue and come to a solution. I myself has been involved in a couple of such debug, and they're pretty challenging and exciting, but very complex. Okay, so testing, apart from testing, we also have to do the qualification, right? Qualification means whatever chip is being given to customer, it should run for a specific time period. They should not have a high mortality rate, right? So both for silicon and package, there are different qualification requirement. So I just listed a little high level view of that. Package qualification needs quite many set of characterization, and device qualification needs different kind of things, right? So for example, HTOL, it is a high temperature operating life. So if a chip design company promises that this chip will work for 10 years, how do they confirm it? So they basically put the chip into an oven which works at a very high temperature, like ambient temperature is 150 degree or 125 degree. So junction temperature reaches to even further high, and they will run the toggling of the scan pattern or MBIS pattern in that chip. So this will accelerate the aging. So whatever we achieve in 10 years by using the device, you can see in 48 hours or 96 hours or in a week. So this testing, this qualification is done on some sample chips. And after this aging is done in HTOL, the device is again tested and checked whether the speed of the chip is now same or it is slower or it is failed completely, right? So that is how the qualification is done. So there are many qualification requirement driven by JDEC, and every chip has to align with that. And this takes several months after first silicon and ensure reliability. And once we pass all this stage, then only a chip can go in volume production and ship to customer. Okay, so coming to toward the end of the presentation, so what are the challenges? We need new fault models for lower nodes, which are more efficient and can reduce test time, can reduce area overhead. The test algorithms are more and more complex now. So again, same challenge: how to implement with simple logic, and also the test time and cost that remains paramount in all this calculation. Debuggability is another important parameter because the fault model itself are so complex, and we have seen even the scan testing has become multiple layers of logic is added after scan chain, so debugging is even more difficult, right? So how do we simplify it or be more accurate in mapping the failure with the fault? and yield analysis. Find out the real issue, silicon issue, process issue by looking at the failure data on the volume devices. Okay. So what is the path forward? Continuous innovation in the testing flow that is happening as we speak. A lot of scope further. This area has been, I think I would say, I've worked in all the areas of SOC design, but this is the most interesting area I actually enjoy working in. I find it most interesting because it has a lot of scope of innovation and it directly adds to the company's bottom line, the profits. Okay, reducing testing redundancy because we are testing it at the wafer, we are testing at final test, we are testing it at validation. So how do we ensure that we are not over testing it, but also still making it 100% tested device? And yield analysis tool and quicker process enhancement. This is further a requirement for, and this keep changing as per the technology node because of the new fault model. So this needs complete uh, day-to-day enhancement, year-to-year enhancement every day. Okay, I think that's all I have. I think you're just bang on time. So I'll see if there are any questions.
Deepak sir, there are some questions from Dr. Aditya Mandloy.
Okay. Oh, sorry, I just saw the slides were not changing. Okay. Yeah, please go ahead with the question. Okay. Is OTP has which bits have fault? Yeah. So OTP essentially has an information. Suppose my memories have redundant column. Okay. That means it has extra column. So during MBIS testing, first I will check which bit has failed. Then I will check which column it is part of, right? More than the bit, I'm more interested in column because I cannot just replace the bit. I have to replace the whole column. So I will take that column information and write into the OTP. So OTP is like a permanent memory. Even if you switch off the power, that will be remaining. Once you switch on the power, the data will remain. So once we switch on power, that uh, the redundant and the faulty column number will reach to the memory logic, memory repair logic. Okay. So anytime anyone try to access that faulty column, that logic will point it to the redundant column. Okay. So which bit, it will always have a faulty column address, not which are available for the fault, because the ones which are available faults are fixed and known by the repair logic. What is unknown is which bits are faulty, and it will change from chip to chip. Okay, so next question is, in same lab we are manufacturing there, only are we doing testing? No. So manufacturing is done by the foundry like TSMC, Samsung, Global Foundries. These are pure play foundries. They basically manufacture the chip. Then they these chips, the wafers, they just manufacture wafers. Then there is another facility which has a lot of testing machine. I think I showed a picture of testing machine. It's a huge machine and cost millions of dollars, and that is a different company or different division. So they will receive the wafer, they will test it, okay, and then it goes to OSAT, basically a package company. So those wafers are cut into pieces. Suppose a wafer has 1,000 chips. So now we have to cut those wafers, and like it's like, when you go for a passport size photograph, you get 8 photos printed on the same card. So it is the same analogy. You will have a wafer. Now you have to cut each picture of yours through scissor and make 8 pictures. Similarly, here each chip is taken out by cutting. We call it saw as a process. So each chip is taken out and then they go through the packaging process, which is happen in the package company or the package factory. So that is another set of machines used for that. Then again, it comes back to the testing facility where the testing is happening of the package chip. Okay, I'll just show the testing machine again. I don't know why it was not showing. Okay. You see this? So this is the example of test system. So there will be, this is for wafer I've shown, but for package testing also will be similar. So this is a test system. It has a lot of compute data. So all the vectors we are generating, they will be uploaded in this. This consider it like a set of CPU, a lot of CPUs, and then after that that will be sent to the prober. Prober will have, suppose this chip has 100 pins, so it will need 100 signals coming out of the test system here. Okay, and those 100 pins will be connected to chip. Okay, so all those signals will be pushed on 100 pins and observed back on those 100 pins, coming back to the test system, where it will compare whether it is matching with the expected behavior or not. Okay, so that is how the wafer testing is done. And during the testing, as I said, right, it might test one chip, and then the probe head will move. It will move to the another chip, then it will move then third chip. That is one way. Or you can also have probe head or the probe card, which can test 4 chip together or 8 chip together. Okay, so that is how the testing is done. So this is like a very expensive device, costs millions of dollars, and that is the reason the test time we spend on this probe or this machine is highly expensive, because they need to take out the cost of the machine from the money they get from the testing the chip. And after a few years, they need to upgrade these machines. Hope it answers your question. Okay, any other question? Okay, thank you all.
Thank you so much, Deepak sir, for your time and sharing such insightful thoughts. It was pleasure having you as our speakers.
Yeah, same here. Thanks to, I'm very happy to talk about it and answer your questions.
Thank you so much.
Thanks.
So should we end the session here?
Yeah, please.
Okay, sir.